Welcome to theme 2.4, where we'll be talking about how we evaluate triple integrals with cylindrical coordinates and spherical coordinates. Because sometimes it's just easier to describe certain volumes or masses in terms of cylindrical and spherical coordinates than with Cartesian coordinates. So we start with cylindrical coordinate transformation, where it's a lot like polar coordinates, where your x and your y went to r and theta, but now your x, y, and z goes to r cos theta, r sin theta, and z. They have the same integrating factor, that is r. If you can't remember the important equations that we used for polar coordinate transformation, you can write them down again because we use the same equations for the cylindrical coordinate transformation. Next, we have the spherical coordinate transformation, where our x, y, and z will be transformed to a rho, theta, and phi. So this is just simplified what we will be doing, and the integrating factor for spherical coordinate transformation is rho squared sine phi. Important relationships to remember are the following. If you want, you can pause the video and write them down because you will be using them quite a lot for the spherical coordinate transformation, or I will be explaining how they get to the equations with the following graph. So, as we can see, phi is the angle between a line or a point to the positive z-axis. Theta is the angle of a point from the positive x-axis. And rho is the distance from the origin to a point. So that's just an easy way to remember. If you can memorize this graph so that you can understand how they derive the x, y, and z in terms of rho, phi, and theta. Some agreements that we've made is that rho always has to be positive and that phi lies between 0 and pi, where your pi will be at your negative z-axis. So to understand this, we will do an example. So the example is as follows. Find the volume of the region above the xy plane inside the sphere x squared plus y squared plus z squared is equal to 16, but outside the cylinder x squared plus y squared is equal to 4. So first, we draw what the region would look like. So in this case, this is what it would look like. You would have your sphere here and your cylinder on the inside. Since they want the volume outside of the cylinder, this is the region that we are looking at, which is outside the cylinder, but still inside the sphere. What we can also get is where these two surfaces intersect. So they intersect at 2 and 2 root 3. So the first thing we'd have to do with triple integrals is choose some place to project onto, some plane. I chose the xy plane, so I let z equals to 0, and that led me to two circles. So the biggest circle is the projection of the sphere, so it has an intercept on the y and x axes on 4, and the smaller circle is the cylinder. So we can first start by doing a cylindrical coordinate integral. So for the cylindrical coordinates, we need to describe the boundaries of r and theta and z. So let's start at r and theta, which we can see from the previous graph. So we know from the previous graph that theta is from 0 to 2 pi because it is a full cycle, and r is in between 2 and 4 because the radius of the small circle was 2 and the radius of the bigger circle was 4. So for z, we have to look at our three-dimensional graph as we've drawn before. So we can see that z would go from the bottom because it's above the xy plane, so it'll start at z equals to 0, and then every time it will go up to the sphere and up to the sphere. So we have to describe this function with z on the one side and x and y's on the other side. So how we did that is we said that z is equal to root 16 minus x squared minus y squared. But since we're doing a cylindrical coordinate transformation, we don't have x's and y's. So we have to transform these x's and y's into r or theta. So we know that x squared plus y squared is r squared, so that left us with the following. So that is done for the cylindrical coordinates. Moving on to how we would do it for spherical coordinates. So spherical coordinates is a bit more challenging most of the time, but sometimes it is easier than the Cartesian coordinates. So for spherical coordinate transformation, we need boundaries of theta, phi, and rho. So from the previous cylindrical coordinate transformation, we know that theta is in between 0 and 2 pi. To get phi, we needed the intercept that we calculated before, and we calculated it to be 2 rho 3. So we know that phi goes from here to here because that is the area that we are working with. So to get phi, where it begins, we will have it going from tan 2 over 2 rho 3. And that's going to be 1 over rho 3, which gives us phi is equal to pi over 6. And we know that phi goes to pi over 2. So the boundary for phi is pi over 6 to pi over 2. The next one we need to get is rho. So rho, we also have to look at the drawing that we had. So we can see that the smallest distance from the origin would be here at the cylinder. So we have to write the equation for the cylinder in terms of rho, phi, and theta to get what rho is at the cylinder's boundary. And we see that it goes from this cylinder boundary to the boundary of the sphere. So we rewrite the sphere's equation in terms of rho as well. So how we do that is as follows. So we know that x squared plus y squared is equal to r squared. And r squared is equal to rho sine phi. So rho sine phi squared is equal to 4 according to the cylinder's equation. So we know that rho is equal to 2 over sine phi. And how we change the sphere's equation, we know that x squared plus y squared plus z squared is equal to rho squared. And that would be equal to 16. So rho is actually technically equal to plus minus 4, but since we say that rho is always positive, it's equal to 4. So the boundary for rho is 2 over sine phi to 4. So the resulting integrals for both cylindrical and spherical coordinates are as follows. For cylindrical, we have theta going from 0 to 2 pi, r going from 2 to 4, and z going from 0 to root 16 minus r squared. And the integrating factor is r. For spherical coordinates, we have theta going from 0 to 2 pi, phi going from pi over 6 to pi over 2, and rho going from 2 over sine phi to 4. And our integrating factor is rho squared sine phi.